Alright, for my first presentation, my name is Austin Kern. We're going to be talking about thin film transistors and the gates that you see at the bottom below, but this one's actually top gated, so it'll be at the top. The PowerPoint didn't, or the presentation didn't really come with the picture for it, so that's just kind of what I found off the internet. The article is called Investigation on Material Selection for Gate Dielectric in Nanocrystalline Silicon, Top-Gated Thin Film Transistor using Ashby's, V-Core, and Topsis methods. And below you can see the authors as well as the journal and the pages along with the year. So the specific scope of the study is it took a closer look at the silicon top-gated part of the thin film transistor. It was originally made out of SiO2, and they're kind of just the key question addressed was what material could they peek around and use that would be best for the gate. Basically, what insulates the material that would reduce current leakage and have better reliability based on material properties while also keeping the device compact. So basically, the SiO2 worked well because silicon was up there in terms of a variable which is actually dielectric constant, that epsilon sub I. But if they reduced the size, it had a couple problems with leaking current, and then it wasn't performing as well. So they wanted to find another material that they could keep smaller and make more compact while improving results. So the main model used was the multi-criteria decision-making process, which is MCDM for short, which is kind of what's on the right there, going from the beginning, which is just generally brainstorming a list of possible materials and then coming up with the final decision. Kind of branching off the multi-criteria decision-making model, the authors use Ashby's approach, which is the approach we've used throughout class, and then also V-Core and Topsis methods. And below you'll see the materials that they actually examined and then the properties that they looked at. And then looking at performance indices, the thin film transistor requires low leakage current and high drain current to maximize performance of the device. So that Pi sub 2 equals is kind of just the main matrix they were looking at in terms of the four properties they were examining, which was dielectric constant, band gap, interface trap density, and band offset. And then the stuff in the parentheses just describes the variables, so you get a better idea. Key result from study number 1. So I talked about it before, but Ashby's method is something we've used in class. It takes one property on the y-axis and compares it on the x-axis, and you see where the materials fall. The only problem with Ashby's is it can provide the best material, but it can't really make a subsequent list of alternatives. So you only see which one is the best, but you don't really see which stacks up second, third, or fourth. Not directly. I mean, you could go through and do that yourself probably, but it's a lot more time consuming. So that's where V-Cores and Topsis comes in, but we'll talk about that in a second. The important process design takeaway was that Si sub 3 and sub 4 is the most suitable material due to a large conduction band offset and low interface trap density. But like I said, Ashby's can't really rank the rest of the materials unless you want to do that yourself. But that's where the second key result comes in, which is the V-Core / Topsis matrix. It actually creates a matrix using equations that standardizes different properties and makes it so you can rank them individually based off just a unitless number. And that's where you see in table 2 material, and then G and R and Q were actually different equations that were put in. And then on the very right you can see the ranking. And V-Core and Topsis both agreed with Ashby's, and then Si sub 3 and sub 4 was the best material chosen. So all of these agreeing would obviously make it important to realize that SI sub 3 and sub 4 was the best. And it is also interesting to point out that this also included silicone, which is what is the gate is originally made out of. So it's important to realize that silicone's an important player. It just kind of depended on what else was added in to the material itself. So key conclusions, like we discussed, seen all three methods, that SI sub 3 and sub 4 was the best material to use for top-gated thin film transistor for better performance and less leakage. My personal critique of this paper, it was a good read with insightful information, and it brought in a lot of properties and variables that I never really thought of. Most what we've gone over in class, we've compared things like tensile strength and density, but these were a lot more specific, and I thought that was interesting. However, some of the variables and equations weren't really explained that well in depth. Also, there was no picture of the device, so it was kind of hard to get a sense of what they were exactly going for. It would have been better if they could throw a picture or a diagram in there of some sort. It was mostly just the graphs that you saw and then these tables. That was pretty much it.